Okay, so let's get started, and then please check your attendance on Blackboard. Okay, so the festival is over. Okay, and then it's time to focus on study, right? So so actually we have I believe we have around uh, 5 to 6 classes until the final exam. So actually, including today's class, I checked. So I think we have 6 classes. Okay, 6 classes left. Then I believe we can take the final exam in the last week of this semester. Okay. So okay. So if you sorry. So it's a time to focus on study. Okay. Okay. So we learned about the test bench design in system Verilog, right? And then I mentioned that this is also very important. So it is because we also take very long time for verifying our design, right? So actually, we can take some time for designing our some system design, but we also need to take a long time for verifying our design, and then we can use test bench file for verifying our design file, right? So we learned how to build how to design the test bench module, right? And then test bench module usually include design on the test. Okay, design on the test is our design module, and then the test bench generate the input signals. So this generated input signals are called input stimulus. Okay, so test bench generate the input stimulus, and test bench monitors the generated output signal. Then match we can match the generated output signal with the correct output values, right? So if the output signals are correct and then it match, the output signals are matched with the correct values, then we can think that, oh, our design is correct. Okay. So this is the verification process. And then also I mentioned that we need to generate the efficient test bench module, right? So we learned that we can design this is the simple test bench module like this example, right? But it's not efficient, right? So in this example, so I just generate the all input signals manually. Okay, so it's not efficient. So we can use the test vector, right? So you can generate the test vector file, and then by reading this test vector file, so we can assign sorry we can assign this test vector inputs to the input stimulus, right? And then this input stimulus is given to the design on the test, and then we can also check the output value, the desired output value with the generated output signals. Okay, then if it's matched, also we can make some code that check the correctness of the generated output values, right? So this is the example. Okay, so you can find that. So this example includes the several system Verilog primitive. Okay, so like functions. So we can use the system Verilog functions like the shop dollar display and the display task or display task. Okay, so we can just check some output values from the design of the test. So actually, like other programming languages, then you need to memorize. You need to memorize the some functions, well, some functions of system value. Okay. Okay, so I will continue teaching the several syntaxes of system value for designing test bench module. Okay, so you can find the time scale, but I believe you are familiar with this time scale. So it is because I already explained about the meaning of this time scale. Time scale, this primitive just define the time unit and time precision. So this is the example. So firstly, with the time scale, you can define the unit of time, right? So this means that the time unit is the 1 nanosecond. So it means if we use a delay number, then it means it means nanosecond scale. And then the second number represents precision of time scale. Okay? We can just represent the time unit within the precision of defined precision. Okay. So this is the example. So in this example, the time unit is 1 nanosecond. Also, you can observe that the precision of this time scale is also 1 nanosecond. But in this example, I use 5.5. So even though I use 5.5 for representing delay in the test bench, this delay will be ignored, okay? Because using a time scale primitive, I just define the precision. Precision of time is 1 nanosecond. So 0.5. So this is not actually this is not allowed, but it's just ignored. Okay, it's just ignored. Okay, so this is the time scale, and then I will show some examples for generating clock and reset signals. So we learned about the D flip-flops, right? And then actually for the digital design, so this is the typical digital design. So you can find the D flip-flops here. So this is the D flip-flops. Then this is also another D flip-flops. You can also observe many D flip-flops. But between these D flip-flops, you can observe combinational logic. So this is the typical form of a digital system. Okay. And then clock is connected to the input of these D flip-flops, and also reset will be connected. So in the previous class, I explained that clock signal is the periodic signal. Okay, it's a periodic signal, and then the 0 and 1 is repeated again and again within clock period. So this is the definition. So this is the clock signal. So this is clock signal. What happened? So this is the clock signal. So in the clock signal, 1 and 0, this signal is replicated, and then in a clock, so the time period, the time gap between the rising edge of clock and the next rising edge of clock, this time is defined as the clock period. So this is the clock period, right? So we normally use symbol T for representing clock period. So this is the clock period. So within a clock period, there you can find the signal 1 and 0, and then these signals 1 and 0 will be repeated again and again. Okay, so this is the definition of the clock signal. So, and then we learned that. So in the test bench, so this is the structure of the test bench file. So this is the TB, and then inside of the test bench module, you can find the design of the test. And then test bench need to generate the input signals, right? So clock and reset signals are also input signals which need to be generated in the test bench module. Okay, so because the clock and reset signal is the kind of important signal, so that's why I explain about the clock and reset signal in this time, right? So let's learn how to generate clock signals. So this is the definition of a clock signal. So inside the clock period, so we need to generate 1 and 0, and then this repeated 1 and 0 needs to be repeated forever, right? So this is the example. So we define clock signal. We declare clock signal. Okay, and then you can find the initial statement. So what is the definition of initial? So initial means that, so at the beginning of simulation, this initial statement will be executed. Okay. So initially, the clock, the value of a clock signal is unknown, right? So I define clock is 0 initially. Okay, so this is 0, and then you can find the forever statement. So forever means that this line, after the forever statement, so this statement is repeated again and again. So this is the meaning of forever statement. So you can find some new statement in the testbench syntaxes. Okay. So, and then in the forever statement, you can find the sharp symbol and clock T divided by 2. So I mentioned that we normally use T for representing clock period. So clock T represents this is the clock period. And what is clock T? Clock T is defined here. Okay, so you can find the defined primitive here. Okay, so actually, so it's the same to the defined primitive in C, right? So it's the same, and then clock T is 10. So what does that mean? So time scale, the time unit is 1 nanosecond. So which means clock period is 10 nanosecond. So clock frequency is 100 megahertz. Okay. So anyway, the clock period, this is the 10 nanosecond. So you can find that. So inside of this delay representation, so clock T is divided by 2. Why? So this is because inside of a clock period, the clock signal is changed from 1 to 0, right? So actually it is changed at the half of clock period. So it's a change from 0 to 1 or 1 to 0, right? So it means you can find that clock is inverse of clock signal. So which means that the signal value is inverted. So initially, clock is 0. So this is the beginning of the simulation. So clock is 0, and then in half of clock period, so it's a t divided by 2. So you can find the here. Then clock signal is inverted. So it was 0, then it will change it to 1. And then after another t of divided by 2, that is clock signal is inverted, right? So it's a 0. So this statement is repeated forever, right? So this is the meaning of forever. So this inversion is repeated forever. So we can generate the clock signal. Okay, so we can generate the clock signal in Testbench module like this. So let's see another example. So I also declare the clock signal here, okay? And then also clock period is 10 nanosecond, right? And then initially clock is 0. So I use the initial statement, but I did not use begin and end. So it is because this is just one line, okay? So this is same to the initial. Begin clock equal 1B0, then end. So it is equivalent. But because I use only one line, so that's why I do not use begin and end. Okay, it's the same to C. So in C, if we just use one line after the statement, we don't need to use brackets, right? So it means, initially at the beginning of simulation, the clock is 0. Okay. So, and then you can find the always statement. Okay. But you can find some different representation. So we learned about the always and at sign, like the always at and sensitivity list. Okay, so we learned about the always and at. Okay, so the meaning of always means that, so if this condition is met, if this condition is true, then always statement will be executed. So this is the meaning of always statement. But instead of at, I use sharp sign, so it represents delay. Okay. So always means that at this delay, clock is inverted. Okay. So in this example, I use sharp sign instead of at for the always statement. So it means that at every delay of time, so delay is the clock t divided by 2, right? Then clock is inverted. So meaning it's the same. So meaning of this always statement is same to the meaning of this one. Okay, so forever. So after t divided by 2, then it's inverted. So 0 is changing to the 1. And then also after t divided by 2, then it's inverted. So we can generate the clock signal. So as I mentioned, when we generate the clock signal, then we need to define clock period, right? So in this example, I define the clock period here, and then after the half of clock period, the clock signal is inverted. Okay, so the initial value is required because initially in system Verilog, all signals are unknown. So I initialize the clock signal first, and then this clock signal is inverted at every t divided by 2. Okay, so we can generate the clock signal. So, and we also need to generate the reset. Okay, so when we learned about the FSM design, so FSM needs to include reset state. It is because we need to build stable system. So during the reset state, the state needs to be defined. That's why we require reset signal. So we also need to generate the reset. So this is the example. So this is another example. But in this example, I generate the clock in a different way. So firstly, you can find the clock on the bar F. What does that mean? F means, so T is the clock period. Then what is F? F is the frequency. Okay, so F is the 1 over T. So, and then, so the clock on the F is defined as 100. So, I mean, so this is the 100 megahertz. Okay. So you can find the clock T here. So I just declare the clock T variable using real data type. Okay, so this means that this clock T data type is clock T is the real number. Okay, so like the floating number. Okay, floating point number. So I calculate the clock on the T, so which means this is the clock period, and then this clock period is represented using a real number. So it's a floating point number. So 10,000 divided by clock frequency, so it's equivalent to 10. So 10 nanosecond. The same. Then, so I declare the clock and reset on the body. So what is on the body? It represents this reset signal is negative reset. Okay. So then we need to generate the clock and reset signal. So you can find that the clock is here, the clock is initialized as 0, and then you can find the always statement here. So the clock is generated using the second method. Okay, second method. Then how can we generate the reset? So this is the negative reset. So this is the clock signal. And then the reset is 0 initially, right? So this is the turn-off state, and then the reset on the bar B becomes 1. Okay, so which means that this is the reset state. So because the reset on the bar B is a negative reset, because the negative reset is 0, then this is the reset state, and then if the reset is 1, then it means that this is the normal state. So we make the reset on the bar B signal. So like the initially reset on the bar B is 0, and then at the some time the reset on the bar B needs to become 1. Then we can define the reset state and then normal state, the test bench. Okay, so this reset we can generate the reset signal like this. So you can find the reset on the bar B is here. So initially, reset on the bar B is the 0. So as I mentioned, reset underbar B is 0 initially, and then it is changed to the 1. Okay. So you can find the delay, time delay here. So it means because the time unit is 1 nanosecond, so after 101 nanosecond, then reset underbar B becomes 1, right? So we can generate the reset signal. So it's initially 0, and then after 101 nanosecond, then reset becomes 1. Okay, so it becomes the normal state. And then question, why 101 instead of 100? So actually, so I will explain about this input generation here. Okay, so usually for the when you generate input signal, then the input signal needs to be changed after edge of clock. I will explain the reason here. Okay, so this is the example of input generation. Also, so actually the clock signal is the periodic signal. Okay, and then reset signal is also a kind of input signal. Okay, so in this example, I will show the example of input generation. So clock signal is here. So in this example, the clock is initially 1, right? It's a different. So what does that mean? At the beginning of simulation, the clock is 1, right? And then after 5 nanosecond, clock becomes 0. So it is 1, and then it's a 0, and then this is 5, and then this is also 5. It becomes 1 and 0, and then its clock signal will be repeated. So what is the clock period? In this example, clock period is, so this is the clock period. So clock period is 10, right? So you need to understand that this number, when your clock is generated, then this delay number is the half of clock period. Okay. And then I explain the reason, right? So anyway, so this is the clock signal. So we can observe the rising edge of clock signal at every 10 nanosecond, right? And then it's a 20 nanosecond, right? And then in this example, so I define the input called start. So this is the start signal. And then start was 0 at the beginning of simulation. It was 0, and then it becomes 1 after 100 nanosecond. So what does that mean? So let us assume that this is the 100 nanosecond. Okay. So start was 0, and then at this time, then start becomes 1 and 0 at 100 nanosecond. What's the problem? So usually, I mentioned that the digital system includes deep flip-flop, and then we use deep flip-flops for sampling signals, right? So For example, so this is the D flip-flop, and then the clock, and then this is the kind of start. Actually, we don't know the inside of this system, but it can be possible. So this is the input signal. So, and then we use D flip-flops for sampling signals, right? So input signals can be sampled by D flip-flops. Then what's the matter? What's the problem? On the rising edge of clock, the input value changes. What's the problem? The problem is that, so I mentioned that using D flip-flop, we sample input values, right? But what is the sampled value on the rising edge of clock? Actually, we don't know. Right? Because the signal value changes on the rising edge of clock. So the exact rising edge of clock. So then what is the sampled value? Is it 0? The sampled value is 0 or 1? Actually, you don't know. So this is the problem. So actually the test bench generates input signals to control. So to provide some inputs. So we can use these input signals for control signals, or we can use input signals for data signals, right? So anyway, these input signals can be sampled by flip-flops. But problem is that if the input values change on the rising edge of clock, then we cannot estimate the exact value of this input on the rising edge of clock. So this is the problem. So usually, I mentioned that the digital system is composed like this, like many D flip-flops, or the combinational logic between D flip-flops. Then usually the input signals are sampled inside of this digital block. So if we generate the input signal inside of a test bench like this, so input signal changes on the rising edge of the clock, then we don't know. Actually, we don't know actual value of this input signal sampled by this D flip-flop. Okay, so that's the problem. So we need to avoid this case. So why do we design test bench? We design test bench to verify our design. So which means the test bench needs to define the deterministic environment. So which means that, so if we do not estimate some exact value of input or some signals, then we cannot use this test bench. The test bench need to generate the deterministic state or deterministic signals. Okay, so that's why we need to avoid this case. So this is the rule. All inputs should be applied with a small delay consequent to the clock edge. So so actually we need to change this delay. Okay. So avoid this case, then I set the delay of input as the 101. So what does that mean? So we can observe rising edge of clock signal at 100 nanosecond, but input is changed at 101 nanosecond. Then if this input is sampled by this clock signal, then at 100 nanosecond, the sampled value is 0. And then at 110 nanosecond, the sampled value is 1. Okay, and then eject. So it's a deterministic. So we exactly estimate the sampled input because we set the delay of input signal as the 101. So should be applied with a small delay. So in this example, the small delay is the 1 nanosecond. Okay, so this is important. Okay, so when we generate the input signals, then this change of input signals is performed avoid the actually the except the rising edge of clock signal. So input is applied with a small delay consequent to the clock edge. Then how about the output? So this is test bench, and then test bench generate the input signals, okay, input stimulus, and then we test bench monitors the output. But we also need to consider when we will monitor the output values generated from DUT. Why? Why do we need to consider the timing of output values from DUT? It's the same reason. So this is the typical digital design. Then you can find that the output of this design is also sampled by flip-flop. So what does that mean? The output value is changed every clock edge. So we cannot find this one. Okay. If we just observe the output signals from a digital system, and then if let us assume that the output signal is the output of deep flip-flop, then we can observe the output signal like this. This is the out, and then this is the clock, and then clock looks like this. Okay, the rising edge of the clock. Then we can observe that the output signal, the value of this output signal is changed exactly on the rising edge of clock. Right? So you can find the rising edge of clock here, but also in this example, you can find that the output values are changing when on the rising edge of clock. So what's the problem? So if we monitor the output values at this time, then what's the exact output value? We don't know with the same reason. So I mentioned that. So I also explained about the input generation. So if the input is changed on the rising edge of clock, we don't know the exact sampled input values. It's the same. So this is the hardware design. So then we need to also determine when to monitor output values. right? So because we need to consider time. So this is very important. So this is some unique feature of hardware design. So we need to consider timing, right? But if we just monitor the output values on the rising edge of a clock, then we don't know. We don't know the exact output values because output will change on the rising edge of clock. So we need to avoid this case. So usually we monitor the output value at the half of clock period. So it means in the middle of the rising edge, okay? The rising edge and then the next rising edge. So at this time. So this is because we can observe that the output signals are stabilized. So we can know the exact value of output signal values, output signals. Okay. So this is the example. Q on the bottom is the output signal from DUT. Okay, so this is the DUT, and then DUT will generate the Q on the bottom signal. Okay, so this is the output port, and then also you can find the Q on the bottom sample. So it means so I will sample this Q on the bottom output signal. But when you can find that so S sign and negative edge flag. Further than mean. So this is the negative edge. Okay. Oh, not this one. So this is the negative edge of clock. And then on the negative edge of clock, I will sample the output. Okay. So Q done is assigned to the Q done on the bar sample. So this is because we need to sample output value in the middle of a clock period, in the middle of a clock edges. So that's why I use negative edge. Negative. So on the negative edge of clock, the output values are sampled. Okay. So this is the rule. So test bench needs to generate the input signal, but the input signal, when we generate the input signal, the generated input will need to be changed slightly after the clock edge. And then when we monitor the output signal, then we need to monitor the output signals in the middle of two rising edges. Okay. So this is actually important. Okay. Okay. So, and then let's learn about the timing control in test bench. So actually this is not an easy part. Okay. So it is because so you can find the many timing related syntaxes, right? So actually I mentioned that these timing related syntaxes are unique features of hardware design. So in a software design, we don't need to consider timing, right? So the values are just changed automatically. But when we design a hardware system, then we need to consider timing of these signals. So that's why the system value includes the many timing related syntaxes. Okay, so we will learn about the timing control in our test bench here. So in this slide, you can find the three different timing control in system value. So like the delay control, sharp sign, sharp symbol. And then we already learned about this sharp symbol in system value. It represents delay. Also, we can find another timing control like the level sensitivity control. Then we can use the weight. And then we can also find the event sensitivity control, like S sign. Okay, so for the timing control, we can use the delay of time directly using sharp symbol. So we can also check the some level condition. So level sensitivity control using the wait statement. Also, we can also monitor the some event. So like this S symbol, so we can define the event of time. So let's see the example. So in this example, I use the weight. So this is the level sensitivity timing control. So I use the S symbol. So this is the event sensitivity control. Then I use the sharp and number. So this is the delay. So what does that mean? So let's see the meaning of these statements. So weight and Q. So I mentioned that this is the level sensitivity. So it means, so if this condition, so we need, so the system value flow will wait until the condition of this wait statement. So what does that mean? So system value monitors the value of Q, right? Then you can find that the value of Q changes at this time from 0 to 1. And then, so this is the condition. So inside of the bracket, you can find the Q value. So it means that it's equivalent to Q is true, right? What does that mean? True means Q is equal to 1. So I mentioned that, so if the signal value is 1, it means true. It's the same to the C or C++. If the signal value is 0, then it represents false. And if the signal value is non-zero, then it represents true. It's the same to system value. So actually, so we are handling this signal. So this signal has only two cases, 0 and 1. So if this condition is true, which means that if the Q is equal to 1, then until, so it means we wait until the Q becomes 1. So it means this is the time when the Q is changes from 0 to 1. So it means the time at this point. Okay, so wait means that, so wait means the system value flow wait until this condition. Do you understand? So we wait here, and then also you can find the at sign here. So at and then positive edge clock. So we are familiar with this representation, right? So we can find this representation. Where is here, like here. So in the always statement, we frequently observe the same representation. But what does that mean? So in the timing control, so it represents the O at this event. So what does that mean? This means at this time. So Q becomes true. And then we also monitor the clock signal. So clock will change like this. So what is the condition? Condition is positive edge of clock. So the system value will wait until at this point, and then at this point, and then we check this condition. So at positive edge of clock, so it means, oh, what is the positive edge of clock after this time? The positive edge of clock is this time, right? So this is this point. Okay, this is 1, this is 1. Okay. Also, you can find another at positive edge of clock. So, which means, oh, wait for another clock, another rising edge of clock. Which means, if this is the 2, then this is means this time. Do you understand? So the wait. So we wait. So it means there is a wait until this condition is true. So if this is 0 and this time is this time. Okay. So Q becomes 1. And then after that, at positive edge of clock, so we wait until the rising edge of clock. So this is point is this timing is 1. Then this is the time at this point. So this is clock signal, and then another at positive edge of clock. So this is another rising edge. So next rising edge of clock. So this is the 2. And we can find the delay. So if this timing is 3, then after 1 nanosecond, right? Then this is this time. This means this time. So what does that mean? It represents we wait until the Q is true, and then after that, we just wait 2 rising edge of clocks, and then after 1 nanosecond, then start becomes 1. So using this different type of timing control syntaxes, then we can control the timing of signal generation. Okay, so this is so it may be tricky because it's somewhat different. So as I mentioned, the time. So we need to consider timing in hardware design. Then this is the unique feature of HDL, right? Hardware description languages. But actually, so you are learning about the hardware design in this course. So you need to understand the timing control of system value. Okay. Okay. So this is another example. So let's estimate this start signal. Okay, you can find that the initial statement is here. So what does that mean? And then initially start becomes 0. So what does that mean? At the beginning of simulation, so t equals 0, then start is 0, right? And then what does that mean? And what can you find? You can find wait and reset on the B. So what does that mean? We wait until this condition is true. It means this is the reset on the B signal, and then reset on the B. Let us assume that is changed at this point, like t equal 11. Okay, right? It becomes 0. It was 0, and then it is 1 because reset is not here. It's nice here. So Which means, so this is the, if this timing is 1, then we wait until this time, right? And then you can find the repeat. What is this one? So another syntax of system value. But also you can find the at positive edge of clock. So actually you can understand that repeat, just to repeat this statement by this number. So what does that mean? It is equivalent to the at positive edge of clock 10 lines of at positive edge of clock. Right? Because you can find repeat 10 times. Repeat 10 times of this statement. Okay, so this is the meaning of repeat. So this is the equivalent to the at positive edge of clock, at positive edge of clock, then so 10 times of repetition. Okay? So what does that mean? It's a clock signal, and then we just wait 10 cycles of clock. Okay. So many clock signals, many clock edges. So we wait many clock edges. So 10 cycles of clock period, clock signal, and until when the rising edge. So after 10 cycles, okay, 10 cycles, because you use the limit 10, then rising edge of clock, so this is the timing 2 here. And then you can find the sharp sign, it's a delay. And then after the rising edge of clock, and then 1 nanosecond delay, then start becomes 1. Okay? So this is the example. So in this example, I use wait and then add symbol and then also sharp symbol. So using these same timing control syntaxes, so we can control the timing of signal. Okay. So actually when we generate the input stimulus, so which means that we need to generate the input signals by time. So that's why we need to understand the timing control in system value. Okay. So try to understand the meaning of this statement. Okay. Okay, so actually this is the important part. Okay, so then we can also use some system value functions like this. It's a kind of some primitive functions. Okay, so in this example we can use in this example. So in this slide, this slide shows the display function and then write function. So display is the one line display. So you can find that the display function here, and then inside of the display you can find some. So so it's similar to the printf. You can find some character arrays, and then like you can percent D. So it means that it's the decimal number, and then it is mapped to this one, and then another percent D, and then it's mapped to the A. So this is the print. It's similar to the print f function, but display just print out the one line of this value, and then write is nearly equivalent to printf function of C. Okay, so you can find that. So this is very similar, but you can find the carriage return. The carriage return symbol here, like a /n, right? So carriage return means that you can just change the line, right? So And then in order to change line in a printf function in C, then we need to use add the /n, right? So actually you can find that, oh, this is equivalent to the printf function of C. It's similar. So operation is done at %d, and %d is the time. Then another %d, this is the A. Okay. So if so it means that the printf is executed at this condition, right? And then monitor. So monitor is a little bit different because so we can monitor display whenever signals change. So actually, this display function, if the display function was write function, can be executed manually. Okay. So in this example, I use the Q on the button, the app. So which means that if the Q dot becomes 1, and then if the Q dot is 1, then this display is executed. So if we use the display function or write function, then these functions are executed manually. But monitor is different. The monitor display whenever signals change. So this is the example. So this is the initial statement, and you can find the monitor here. So which means that this monitor function is executed initially. And then this monitor function monitors the A and B, right? So if the A and B values are changed, then this monitor display the value of A and B, right? So the display whenever signal changes, then we can use monitor function. Also, so you can find, so we can just control the simulation. So if we just, so you can find the start function and then finish function here. So these functions are used for stopping or used for finishing our simulation. So if we do not define the start or finish of our simulation, then the simulation will continue forever. Okay. So we can just use stop for stopping our simulation. So it's just end simulation. So stop is just stop. So simulation just ends. Okay. So it's different. So we can use also finish function. The finish also end simulation and exit simulation. So if we use just the stop, then the simulation is just stop. And then if required, then we can restart. So we can just continue the simulation at the stop point. This is the meaning of stop. But finish. If we use the finish function, then simulation stops and simulation ends. We cannot resume simulation at the stop point if we use finish function. Okay. So we can control the simulation using start function or finish function. So this is the example. The Q done. So using the always statement, I just check the edge. So like the value of Q done. Okay, the value of Q done. Then if the Q done is 1, exactly 1. So if we use the 3 equal sign, then it's the exactly. Okay. Then the operation is done. So this line is displayed, and you can find the stop function here. So what does that mean? If the Q done, so this is the Q done, Okay, and then the Q dot becomes 1, then at this time, these characters are displayed and simulation stops. Okay, so simulation stops at this point if the Q dot becomes 1. So as you can estimate, so Q dot signal is the down signal. Okay, so just the output signal, but you can just estimate that, oh, we can use the down signal for stopping the simulation. Then if the down signal is detected, then it's stop. Simulation is stop. So we can also use the file IO in the test bench. Like, so like actually the syntax is very similar to C. So system Verilog supports the file open function as like f open, and then file close function as f close. And then so we can read some values from file using the f scanf. So if you are familiar with the C, then you can find the equivalent function in C. Like so actually the name is same. Names are the same. So C also includes the f open function, f close, and then f scanf. And then if we want output to generate output to file, we can use the f display and f write. Okay. So you can find so for the file IO, can add the f. So this is the example. So actually in C, we need to define the file pointer using file, but in system Verilog we use integer. Okay, because in the system Verilog we cannot find the pointer type. So actually the C or C++ support pointers. So and then actually we use declare file, so which means that it means we declare file pointer. But in system Verilog, the pointers are not supported. So we just declare the file pointer as integer. Okay, so actually this is the file pointer. It's assigned to some file pointer here. But we just declare the file pointer as integer. So, and then using the fopen function, then the file is defined. So file is opened for write. Okay, and then the Q done, then we use the f write instead of write, right? And then we like the C, the file pointer follows f write. Okay, that's the same. So if you read the test bench file I provided, you can find this part, right? So you can observe that when the test bench is executed using the Icarus Verilog, then this Icarus Verilog generates the .out file. So it is because I just declare the files for write, and then I use the fwrite functions. So if you are interested, then you can just find the provided test bench file. Okay. We also use the fscanf, like the fscanf function in C. Okay. Here. And then system Verilog supports the task. So sometimes some statements can be repeated, right? But so if some states are repeated, then we can define task. Okay. So if a certain part is repeated, then we can define function and then we can call function in C. So it's the same. So for the repeated part, we can define task, then we can call task in system value. So this is the example. So it's very similar to function of C, and then but task can have multiple inputs and outputs. Okay, so this is the zero count task. Then if the zero count is code, then this part is executed. System value also support function. So it's similar to also a function of C, but function must have one output. So in the test, you can find the multiple inputs and outputs. But in function, then you can find that function does not have any output here. Okay, but you can find the function name is used as the output. Okay, so and then okay, so we are almost there. So some tips for FSL design. So actually, so for this, so you know, I posted the third lab assignment, and then in the third lab assignment, you are requested to design FSM, right? But if you read the skeleton code, like the FSM 1.sv, you can find this part, okay, inside of the skeleton code. So these are just some tips for FSM design. So in the waveform cannot represent the characters. Actually, it is because the system value just handles bit data. Okay, only bit data can be displayed on the waveforms. But for the FSM design, it's not convenient. So which means, if we just see the FSM, so states like the 000, 001, 110, then actually it's not easy to recognize the states using the state represented using binary numbers. So it's because we are familiar with the characters, not binary numbers. So we can use this statement. Okay. So if we add this statement, then state will be displayed. State will be displayed using characters. But you can find that another state variable is defined, and then actually based on the state, then state of the debug represent some state name. Then if you just select the state of the debug in the waveform, then you can find the state name, the waveform. But you can also find the synthesis translate off. So it is because this part is included in your source file. But as I mentioned, we just write system value source code file for designing hardware. But this part is included just for simulation. So in this case, we can just use the synthesis primitive, like the synthesis translate off. So as you can estimate, at this point, translation is turned off for synthesis. Then synthesis tool just read the system value code, and then at this point, the synthesis tool just ignore this code until and the synthesis tool encounters synthesis translate on. Okay, so if you just read the skeleton code I provide for the third lab assignment, then you can find this part. But it's just a key. Okay, so I'll stop here. Any question? Thank you for your attention. 감사합니다.